Hello, and welcome to my presentation on 3D printed morphing wings for controlling yaw. My name is Ben Moulton. I am a master's student. I work with Dr. Hunsaker in the mechanical engineering department at USU. So if you've ever looked out the window of an airplane, you've probably seen what's pictured here. You can see out in the background a beautiful view, but what I want to focus on is the airplane wing with the control surfaces, and which is going to be the majority of what we talk about today. So you can see here a control surface on this wing. It's basically a flap. You probably saw them deflected during flight. Here's another control surface. And so an aircraft uses those control surfaces to control itself during flight. So there's three principal axes of motion for aircraft that I want to focus on today. One is roll, which is shown in the top left. It's where you've got wing up, wing down. And so that's more or less controlled by ailerons, which are control surfaces out at near the tips of the main wing. The second is pitch, which is a nose up, nose down, generally controlled more or less by the horizontal stabilizer out here at the back of the tail. And the third is yaw, which is nose left, nose right. And that is more or less controlled by the vertical tail. And so something that, we're always pushing for more efficient aircraft. One thing we can do is get rid of these vertical and horizontal control surfaces. And getting rid of those decreases the drag on the aircraft. And so if we get rid of those, we decrease the drag. But what about how do we control this aircraft? How do we control it in yaw without that vertical stabilizer? And that's what I want to focus on today. And one solution that's been proposed is to have several control surfaces along the wing and use those control surfaces to create more drag on one side than the other, or excuse me, create drag with a larger moment arm on one side than the other, thus causing the aircraft to yaw to one side or the other. So in order to do this, first we need to talk about the differences between traditional flaps and parabolic flaps. Traditional flaps are what you generally see on most, small scale aircraft. They just have a single hinge point, single rotation, and after which it just rotates about that point. A parabolic flap, on the other hand, has a hinge point, but it curves to form a parabolic profile and that's conforming camber line. So it's making sure it's the most efficient after that hinge point. And so on the left, or excuse me, on the right are shown the comparison of these two flaps in their efficiency. It's what's called their flap effectiveness. So with the circles, you can see a traditional flap, with the squares, a parabolic flap. For the same size flap at the same condition, the parabolic flap would be more effective. In other words, it creates less drag and it has greater controllability. Is the long run of the story there. And so here we present two designs, the ARC's design and the Kinks design. The top being used with one type of control surface, the bottom, the Kinks design, being used with another type of control surface. And so what you can see here is they have kind of these flexible arcs, these not so flexible kinks, that when you pull on the tongue, it deflects the wing down, pull on the tongue, deflects the wing down. And so, like I said, with each one, you have two different types of, with each one, you have a control surface type. With the ARC's design, you can create a continuous control surface. In other words, the trailing edge, that back of the wing, is completely continuous along the wing. And on the right, you have a discrete control surface. In other words, there are multiple control surfaces that are not connected together. So you can see discrete changes along the wing of those control surfaces. And so a study that will be published in future by a couple of my colleagues looked at the yaw control characteristics of a wing that has discrete control surfaces versus continuous control surfaces. And they found that the discrete control surfaces have greater yaw controllability. And that's because of the increased drag by these distinct section shifts that you can see right there. The greater the drag increase, the greater you're able to control the yaw on the aircraft. Shown here are the parabolic deflections of the ARC's mechanism on top and the Kinks mechanism on bottom, deflected to positive and negative 15 degrees. And so you can see that they're able to to deflect following that parabolic profile. Shown here is the ARCS mechanism on a continuous control surface wing design. And on the right is the kinks mechanism on a discrete control surfaces design. And so you can kind of see that continuous trailing edge right there. And over here, the discrete disconnected trailing edge. And so, like I said, we ended up choosing the discrete flaps because they were better able to control yaw than the continuous control surface. And shown here is the airfoil mechanism design that we ended up with. And on the bottom is the Horizon aircraft, the airframe that we're going to test this yaw controllability on. You can see the cosine clustered control surfaces and that each one has a distinct control surface, or excuse me, a discrete control surface. Shown on the left once again is the Horizon discrete kinks control surfaces. And on the right is are the deflection values that we're able to get out of these discrete control surfaces. We were able to get plus or minus 25 degrees, which is a little bit more than what we'd need in order to control yaw for this RC aircraft. 3 other tests that we ran. The first was a fatigue analysis, which was just to actuate the wing back and forth, like you see in the GIF there, to make sure that the wing mechanism basically wouldn't break while we were flying around. You want to make sure that you can control the aircraft. So we actuated it up to about 15,000 cycles for one test, and I believe about 25,000 for the other test. And we figured we just stopped it right there. Just mechanism was doing fine. We just knew that we wouldn't encounter more than those numbers of cycles on a single RC flight. In the middle, you can see a picture of a load test that we performed. Basically what you do, you stick the wing in between 2 tables, you put a whole bunch of weight on it to make sure that it's able to support the forces and moments that you're expecting during flight. And then you can load it up to failure, meaning you put as much weight on it until it breaks to make sure that that the weight and moment that it will break at won't be encountered during flight. And the third test we performed was a parabolicity study where we compared the outside of these airfoil shapes, these parabolic deflections, to that which we would expect from an analytic outline, basically from equations. We compared the outline between the two, and those are the results that we show here on the right. So in conclusion, we present the ARCS design with continuous control surfaces and the kinks design with discrete control surfaces as potential solutions for controlling yaw. And we present the kinks design with discrete flaps as the design that will control yaw better. And shown here in the picture is the Horizon airframe, once again with the cosine clustered control surface, discrete control surfaces using the kinks mechanism. Thank you for listening. For more information, please check out my thesis, which will be on digital commons. Also check out my SciTech presentation, and also to look up the code for how we made those mechanisms and the 3D printer part files for the aircraft. You can check out the lab website at aerolab.usu.edu. Thank you.